Hello, everyone. Welcome back to another video. In this video, we're going to be taking a look at a question from IB Chemistry Paper 2HR from the November 2017 batch. And this question is all to do with periodic trends and in particular, melting points. So questions like these come quite frequently. And really in this, it's more about understanding and even to some extent, remembering information rather than solving a problem or creating a math sum. So if you understand the concept behind this, then you can solve any question relating to it. Now, they've asked us, explain why the melting points of group 1 metals decrease down the group, whereas the melting points of group 17 elements increase down the group. So let me just draw what they mean. So example, this is the periodic table. Just imagine this is the periodic table. We have group 17 over here, which are the halogens. And then we have group 1 metals over here, which are the alkali metals. So alkali metals start with lithium. And as you go down, eventually you reach cesium. There are many other metals along the way. You have potassium, you have rubidium, you have a bunch of other metals. So you can just take a look at a periodic table and get an idea. As for group 17, they are the halogens. It starts with fluorine and it goes all the way down to iodine. And in the middle, again, you have a bunch of other elements like chlorine, bromine, etc. So as you move down the group, we happen to see a trend in both fluorine and lithium, in both group 17 and group 1. And it's to do with the melting points. We begin to see that the melting points of group 1 decrease, whereas the melting point of group 17 increases. Now, why does this happen? What is the reason? That is what they're asking us in this question. And to really understand what goes on, you need to first understand what exactly happens when you melt something. Because remember, they're asking about the melting points. So what is happening when you're melting something? Now, imagine I have given you a chunk of some substance. Okay, I've given you a chunk of gold. Just imagine I've given you a chunk of gold. And if you really take the gold and you zoom into it, right, you put it under this really, really powerful microscope. I don't think microscopes exist, microscopes as such exist, which can see atoms. But imagine you have such a microscope and you zoom in really, really closely into the solid gold chunk, and you begin to see these little circular things. And these would be your atoms of gold. So each of these atoms is a gold atom, Au. That's the symbol of gold in the periodic table. So each of these individual atoms are gold atoms. Now, when you want to melt this gold, if you want to make this, you want to turn this gold into liquid gold, right? So that you can coat different things with it and make nice jewelry or watches or whatever, right? What you're essentially doing is that you are breaking the bonds between these gold atoms, because this structure, this highly stable or highly organized structure, right? It looks like a square, it's a lattice, right? This structure does not happen spontaneously. It just doesn't exist. It happens because there are certain bonds between the elements. So if you look at just these two, if you zoom in a bit closer into just these two atoms, you'll see that between these two gold atoms, there's something like a chain, which is holding them together. You can think of it like a chain. I know it looks like an infinity sign, but you can think of a chain being here. So it's holding them together. And this is the chain. And these chains in chemistry, we refer to them as forces, right? Different kind of forces. And when you want to melt something, what we're essentially doing is we are breaking these forces, we are breaking them away so that now these two gold atoms are free to move around, right? That's why you get something called a liquid. So they're free to move around, but the force is not entirely broken. Some form of force still exists, but the main force, the strong force that holds them together in that organized structure is gone, but still some force exists. So then you get something called liquids, where there is some sort of structure, but it's not organized at all, right? It can be rearranged and reshaped. That's why liquid is so malleable. So that gives you gold, liquid. And this is true for most elements, right? This is exactly what happens. You break the forces that are holding atoms together. Now, I have used gold in this example, and hopefully you understand what I've said. What about in the case of the elements that we are talking about in this question? What about lithium and fluorine or cesium and iodine? What is happening over here? So for lithium, it's a group 1 metal, and the forces that hold metals together, the bonding in these elements, is called a metallic bond, right? And really what this solid is held to in the case of lithium, right? If you have different lithium atoms, now what these dots are in the middle, I'll get to in a bit. So imagine this is a solid lithium bar. This is a solid lithium. And each of these circles are lithium atoms. And they're all held together in this organized structure by electrostatic attraction between positive ions in this structure and delocalized electrons. Now, what on earth is this? What does this mean? So these dots in the middle, these are delocalized electrons. What are delocalized electrons? Delocalized electrons are basically electrons that are shared not between two atoms, but over multiple atoms. They are like a public service, you can think of it. So for example, things like public transport in your country, right? No person in particular owns it, but everybody uses it, right? And similar to that, delocalized electrons are with the exact same function. They don't belong to one particular atom, but they're used by everybody to maintain this stable structure. And how does that exactly happen? How do we get these delocalized electrons? Well, obviously you only get delocalized electrons if every single lithium atom has given off one electron and it has contributed to the pool of delocalized electrons so that everybody can use it, right? And when each of these lithium atoms lose one electron, naturally they get a slight positive charge, right? Because that's what happens. These become ions, these become lithium ions. And because they have their nuclei has a slight positive charge, and electrons, as you know, these dots in the middle, electrons carry negative charges, positive and negative attract each other. So you see a force of attraction occurring between the positive nuclei of these lithium atoms and the delocalized electrons. So the delocalized electrons are attracting the positive nuclei of the lithium atoms and lithium ions, and it's holding them together. And that's why it's called an electrostatic force of attraction. That's the force that holds together this lattice structure of lithium. And similarly, all the other group 1 metals are also bond in the same way. They bond in the same way. So why does it decrease? Why does the strength of this electrostatic attraction decrease as you move down? Remember, this force between the electron and the positive nuclei of the lithium ions is called an electrostatic force of attraction. So why does it decrease as you move down? And the reason it decreases is because the ionic radius increases. Now, what is ionic radius? Basically, ionic radius is, like you can think by the name, it is the distance from the nuclei to the outermost shell. I'm sure you've learned about this in math, you know what a radius is. So it is from distance of the nuclei to the outermost shell. And as you move down a group, we see that each consecutive element has gained one more shell, right? Because group 2 elements have 2 shells, group 3 elements have 3 shells, group 4 elements have 4 shells, group 5 elements have 5 shells, and so on. So as you move down the group, we begin to see that the number of shells is increasing, and consequently, the ionic radius will also increase, right? So imagine you have lithium, right? Lithium, I believe, has two shells. So lithium has the inner shell, and then it has one more shell. So this lithium has distance. Sorry, my apologies. Lithium has only one shell. So this lithium, its ionic radius is this small. Now imagine I put another one on it, and this lithium is now actually, I think it's potassium, I believe, because I haven't memorized the periodic table on the top of my head, so I can't really remember. But as you move down, you see that the ionic radius begins to increase. And now if it becomes something like cesium, if we make a jump all the way to the down, it's even bigger, right? There's so many shells. So the ionic radius increases tremendously, becomes much bigger. The whole atom becomes bigger as a whole. And when the whole atom becomes bigger, right, when there are more and more and more shells, and in this structure that we have seen over here, where the positive nuclei is attracted to the electrons, and that's the force holding them together, the electron that is outside the ion also becomes further and further away. So imagine this is the electron. Look how far that has become now. Whereas if this was just lithium, right? If this was just lithium, the electron would be right here. It would be so much closer, right? And consequently, if it's closer, the force of attraction will also be stronger. If it's more far away, the force of attraction is weaker. But if it's closer, the force of attraction is stronger, right? That's common sense. That's logic. So as we move down, and as the ionic radius of each consecutive element in group 1 increases, we see that the electrostatic force of attraction that holds the lattice structure of solid group 1 metals together gets weaker and weaker and weaker, because a positively charged nuclei of the group 1 metal ion is becoming farther and farther away than the delocalized electrons in the structure. And at the end of the day, these delocalized electrons are the glue that holds the structure together. So if the force is getting weaker, your glue is getting weaker. And if your glue is getting weaker, your structure is easier to break. So it requires less heat energy to melt it. There's less force required to break this apart. That's why melting points in group 1 metals, as you go down the group, decrease. Hopefully that makes sense. Now, the answer that you should put for this, it should be, of course, more technical. You can't go into such detail like I have explained. You have to put a very concise statement, and you can say that the force of attraction, between metal ions and delocalized electrons. I'm just going to call it DE, delocalized electrons, because I won't have enough space to write it. And delocalized electrons decreases. So that would be your answer for why the melting point decreases as you go down group 1. It's because the force of attraction between metal ions and delocalized electrons decreases. And you can also add a reason stating that this is because the ionic radius of the metal ions increases as you go down. You can put that as well. But really, that's up to you. If you want extra details, sure, go ahead. It's good. But if you want to save time, just put this one concise answer. Now, what about group 17? Group 17, it flips. It's the opposite. Now, it actually increases as you go down. So why does that happen? And again, it's all to do with bonding. It is completely to do with bonding. However, in group 17, we do not have electrostatic force of attraction. Metallic bonding doesn't exist, right? Like I showed you right now. There is no delocalized electrons. There is no ions. There's none of that. Group 17 elements bond in a different way, right? So if you want to imagine it, you can imagine that there are two people over here, right? And if they want to hold each other, they can hold each other's hands, right? They can hold each other's hands. So this is one form of bonding. However, another group of people, maybe they're feeling a bit creative, and instead of holding hands, they hold each other's legs. I don't know, okay. I just made up some weird example, but this is to give you an idea that different types of bonding do exist in different elements between different elements. So there is different types of bonding, and each of these different types of bondings come with their different characteristics and different strengths. So naturally, you could consider that holding hands is a stronger way of bonding than holding each other's legs. Okay, so that's just to show that each of them have their different characteristics, different requirements, and different strengths and different weaknesses as well. And similarly, group 17 elements bond in a different way. Group 17 elements bond with each other by something called van der Waals forces or London dispersion forces, right? London dispersion forces is a type of van der Waals force. So what exactly is that? What do I mean when I say that? So because halogens, like group 17 elements, they can't exactly form forces of attraction like metallic elements like lithium or cesium. That doesn't happen, right? There's a difference. So what happens is that forces called London dispersion forces occurs between the molecules of halogens. Now, halogens can't exist singularly. So you can't just have one molecule of chlorine which is satisfied or which can exist by itself. We don't find that naturally. Chlorine, they exist as diatomic molecules. So they exist like this. I'm sure you have seen this in your textbook somewhere, chlorine, right? Or you have fluorine for that matter. They exist like this. They exist as diatomic molecules. And in a solid structure, many of these guys, many of the halogens are not found in solid structures, or they're found in solid structures at very, very low temperatures. And that's because van der Waals forces are extremely weak forces. London dispersion forces, very weak forces. They're not as strong as metallic bond or electrostatic force of attraction. They're very weak. And this is how they occur. So imagine you have a fluorine atom. This is a molecule of fluorine. And over here, you have another molecule of fluorine. And now, as you know, fluorine, these guys are really, they have a lot of electrons, right? They have 7 electrons. So they have 7 electrons, and that's a lot of electrons. So what ends up happening is that, wait, let me just make sure I have the right amount of electrons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Oh, that's interesting. Anyways, so because they have so many electrons, and electrons, as you know, are in constant movement. These electrons are not stationary, right? They are constantly moving around. They're whizzing about and here and there and everywhere, right? It's random. It's extremely random. They're not organized. So what occasionally happens is that all the electrons in the atom at one moment, one small chance, they happen to gather around in one particular side of the atom. So in this case, let me just draw that better. Actually, this is a bit confusing. So, and one particular point, fluorine is bonded to another fluorine. And this fluorine, it's an atom. And this fluorine, the electrons in this fluorine, at one random moment, right, all the electrons of this fluorine happen to gather upon this side. They gather on this side because remember, electrons are in constant movement, random movement. So this side, which is left empty, this side of fluorine, which is left empty and doesn't have any electrons, gains a slight positive charge. And another fluorine atom molecule, which is close by, if all of its electrons are in one specific spot, this is obviously more negative, right? It's a negative side. And we know that positive and negative attract each other. So these positive and negative forces, because of this temporary arrangement of electrons, we see a force of attraction occurring between these two molecules of fluorine. And now this is a very weak and very temporary force. The moment the electrons rearrange, the moment they go back in a different position, this bond erases, it breaks. And then this fluorine will go and make a similar, by chance, make a similar bond with another fluorine molecule. And this fluorine will go and by chance make another fluorine bond with another fluorine molecule. Hopefully, that's the gist of how the bonds are formed in halogens in group 17 elements. And this happens for all of the group 17 elements. This is called London dispersion forces, and you can also call them van der Waals forces if you like that. Now, when you are at the top of group 17, like fluorine, right? Fluorine is a very small atom. It doesn't have many electrons, right? It has a smaller mass. It's not as heavy as iodine, and it has fewer electrons as well. So the chances of this arrangement happening, this phenomenon where all the electrons gather on one side and there's a slight positive charge on the other side, and likewise all the electrons gather on one side and there's a slight negative charge on another atom, the chance of this phenomenon happening is smaller because obviously it has less electrons. However, as you move down the group 17, number of electrons of each element increase, and consequently, the chance of this van der Waals or London dispersion forces forming increases, right? And that's why the melting point of iodine is higher than the melting point of fluorine, because the London dispersion forces, as mass and number of electrons increases, London dispersion forces become stronger. And that is it. That is the reason. So if you want to write your answer for why the melting point increases as you move down group 17, you can say that number of electrons increases. You can also write molar mass increases, because remember, iodine is much heavier than fluorine is. And that's another thing that London dispersion forces is dependent upon. The heavier the atom, the heavier the molecule, the stronger the London dispersion forces. So another reason is molar mass increases. And this leads to stronger London dispersion forces. LDF, I'm going to keep it as London dispersion forces, but please do not write short forms in the exam, write out the full thing. I have written the short form because I don't have enough space, but don't forget to write the full form in the exam. Hopefully you've understood this. I know the last part where I explained van der Waals London dispersion forces can be a bit tricky, a bit difficult to understand and conceptualize, but please, if you have any questions regarding this, feel free to reach out to me on my social media, put it in the comments below, send me an email. I'll be more than happy to help you. I really appreciate all the content interaction I'm getting on my Instagram page. It's crazy. I started this as a hobby, just for fun, but eventually this has turned out to be something so much bigger. And so many students reach out to me, and it really makes me happy to help you all. So please feel free to reach out to me. I'm always there to help. Thank you for watching. Take care of yourself, and I'll see you in another video with another question.